Welcome to Cambridge IGCSE Physics, Lesson 48.1, Inducing EMF. EMF stands for electromotive force, which we'll explore in detail today. This is core content for your examination. Let's examine our learning objectives for today. By the end of this lesson, you will be able to know that a conductor moving across a magnetic field can induce electromotive force. Know that a changing magnetic field linking a conductor can induce electromotive force. Understand electromagnetic induction principles. These objectives align with Assessment Objective 1, Knowledge, Assessment Objective 2, Application, and Assessment Objective 3, Experimental Skills. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, electromagnetic induction, which means the process where a changing magnetic field induces electromotive force in a conductor. Second, induced EMF, which means voltage generated by changing magnetic flux through a conductor. Third, moving conductor, which means a wire or metal rod moving through a magnetic field. Understanding these terms precisely is crucial for examination success. Let's explore our first core concept. The fundamental principle states that when a conductor moves across magnetic field lines, electromotive force is induced. This means the conductor cuts through magnetic field lines, causing electrons to move. The definition is, electromagnetic induction occurs when magnetic flux through a conductor changes. Key factors affecting induction are speed of conductor movement, faster movement induces greater EMF, strength of magnetic field, stronger field induces greater EMF, and length of conductor in field, longer conductor induces greater EMF. The diagram illustrates a conductor moving through a uniform magnetic field B with velocity V, inducing current Y. Now we examine the experimental method. This follows Cambridge IGCSE standards. The apparatus needed includes a bar magnet with clearly marked north and south poles, a coil of wire with multiple turns, and a sensitive galvanometer to detect small currents. The method consists of these steps. First, connect the coil to the galvanometer. Second, move the magnet toward the coil at constant speed. Third, observe the galvanometer deflection. Safety is paramount. Handle apparatus carefully to avoid damage and avoid short circuits. The diagram shows the complete setup with the magnet moving toward the coil, causing the galvanometer to deflect. Let's work through our first example. The problem states, a conductor of length 0.5 meters moves at 2.0 meters per second, perpendicular to a magnetic field of strength 0.1 Tesla. Calculate the induced electromotive force. We are given length equals 0.5 meters, velocity equals 2.0 meters per second, magnetic field equals 0.1 Tesla. We need to find the induced electromotive force. Step 1. Write the equation. We use the motional EMF formula, which is epsilon equals BLV, where epsilon is induced EMF, B is magnetic field strength, L is length, and V is velocity. Step 2. Substitute the values. We write epsilon equals 0.1 Tesla times 0.5 meters times 2.0 meters per second. Step 3. Calculate. 0.1 times 0.5 times 2.0 equals 0.10. Step 4. State the answer. The induced EMF is 0.10 volts to two significant figures. Example 2 applies Faraday's law to changing magnetic flux. The problem is, a magnet approaches a coil, causing magnetic flux to change. The data shows flux changes from 0.02 Webers to 0.08 Webers in 0.5 seconds. Now we analyze. First, calculate the flux change. Change in flux equals 0.08 minus 0.02 equals 0.06 Webers. Second, apply Faraday's law. Faraday's law states that induced EMF equals negative rate of change of flux. Third, calculate. Induced EMF equals 0.06 divided by 0.5 equals 0.12 volts. Fourth, state direction using Lenz's law. The induced current opposes the change causing it. The graph shows the linear increase in magnetic flux over time. Mathematical skills are crucial in electromagnetic induction. Let's examine three key skills. First, Faraday's law. The general formula is epsilon equals negative n times d phi by dt, where epsilon is induced EMF, n is number of turns in coil, and d phi by dt is rate of change of magnetic flux. For constant rate of change, this becomes epsilon equals negative n times delta phi over delta t. Second, motional EMF. The formula is epsilon equals B LV for a conductor moving perpendicular to a magnetic field, where B is magnetic field strength, L is length of conductor, and V is velocity. Third, unit analysis. We can check our answer by verifying units. Tesla times meter per second equals volt, which confirms our calculation is dimensionally correct. Now practice what you've learned with these three questions. Question 1 is basic level. It asks, a wire of length 0.3 meters moves at 1.5 meters per second in a magnetic field of 0.2 Tesla. Find the induced EMF. Question 2 is intermediate. It states, a coil has 50 turns. The magnetic flux changes by 0.04 Webers in 0.2 seconds. Calculate the induced EMF. This requires you to apply Faraday's law with multiple turns. Question 3 is advanced. The question is, explain why moving a magnet away from a coil induces current in the opposite direction compared to moving it towards the coil. This tests your understanding of Lenz's law. For all questions, remember to show you're working clearly, include units in every step, and check your answers make physical sense. Physics principles power our modern world. Let's see how electromagnetic induction applies in practice. In generators, rotating coils in magnetic fields convert mechanical energy from wind or water into electrical energy for our homes. The changing magnetic flux through the coils induces the EMF that powers our devices. In transformers, alternating current in the primary coil creates changing magnetic fields that induce voltage in the secondary coil, allowing us to change voltage levels for efficient power transmission. In induction motors, changing magnetic fields induce currents in rotors, producing the rotational motion that powers everything from washing machines to electric vehicles. These applications show why physics matters. Career-wise, understanding electromagnetic induction leads to opportunities in electrical engineering, renewable energy systems, and power grid management. Let's review the solutions. For question 1, we use the motional EMF formula. Epsilon equals B LV equals 0.2 Tesla times 0.3 meters times 1.5 meters per second equals 0.09 volts. For question 2, we apply Faraday's law with multiple turns. Epsilon equals N times delta phi over delta t equals 50 times 0.04 Webers divided by 0.2 seconds equals 10 volts. For question 3, we explain using Lenz's law. When the magnet moves away, magnetic flux through the coil decreases. By Lenz's law, the induced current flows in a direction to oppose this change, creating a magnetic field that tries to maintain the original flux. Now, exam success tips. Always show you're working step by step. Include units in every calculation. State the relevant laws. Name Faraday's law for flux change problems and Lenz's law for direction questions. Draw clear diagrams showing magnetic field directions and induced current directions. Let's summarize today's lesson. The key points to remember are, first, for a moving conductor, the induced EMF equals BLV when the conductor moves perpendicular to the magnetic field. This formula applies to straight conductors cutting through uniform magnetic fields. Second, for changing magnetic flux, Faraday's law states that induced EMF equals negative N times the rate of change of flux, where N is the number of turns. This applies to coils experiencing changing magnetic fields. Third, Lenz's law tells us that induced effects always oppose the change causing them. This determines the direction of induced currents. For further study, practice calculating flux changes with coils at different angles to magnetic fields. Review how these principles apply in generators that convert motion to electricity and transformers that change voltage levels. The next lesson covers alternating current generators and motors, which build directly on today's electromagnetic induction principles.